Okay, good evening, everyone. So we'll continue from where we left yesterday. Okay, so we discussed about arguments of a complex number. All right, yesterday we, properties associated with modulus and argument, modulus and argument of a complex number. So today we'll discuss this, finding the modulus and argument of complex numbers. So problems we'll do. Okay, so find the modulus for all these questions. It is this: find the modulus and argument of the following. First, z is equal to okay, sorry. Z is equal to 1 plus root 3i. Okay, let's find the modulus and amplitude. All right, for z is equal to under root of a square plus b square. Mod z, if z is a plus ib, then modulus is under root a square plus b square. And argument of z you have to verify. It is 3 cases. It is tan inverse b by a, or tan inverse b by a if this is when a greater than 0. Then you have tan inverse b by a if A negative, B positive, so it will be tan inverse B by A plus pi. Tan inverse B by A minus pi if both A and B are negative. Okay, this is the, so now let us do this. So Z is equal to 1 plus root 3I. So modulus of Z will be under root of 1 square plus root 3 the whole square. This is 1 plus 3, 4, that is 2. So modulus is 2. And argument, now both A and B are positive. So you get tan inverse of B by A. Now what is tan 60? Tan 60 is root 3. So tan 60 is root 3, or tan pi by 3 is root 3. So tan inverse root 3 is 60, or pi by 3.
So what does tan inverse mean, sir?
Oh, see, very simple. From, from two sets AB, X relates to Y. Like here, and there's a function. Here function is tan,
Yes, sir.
and tan 60 is equal to root 3. We know this. So this is our X, this is our Y. Now inverse function is that function which relates the opposite. So here Y will be tan inverse. So 60 is tan inverse of root 3. Inverse function, that's all. This
Okay,
function
okay, yes, sir.
relates
Got
X
it.
to Y.
That other
This is,
function relates y to x.
yes, that's all.
Got it, sir.
Okay. So this is pi by 3. Or other way, if theta is the argument, then tan theta is B by A, like that. So this is root 3, which implies theta equal to pi by 3. This also you can do. Okay. So tan inverse is just the inverse function, like this. So this is the modulus and this is the argument. Modulus is 2, argument is pi by 3. Now same question we will change. This is, that is uh, minus 1 plus root 3, right? Now I'll do minus 1 plus root 3I. Okay. Now what happens to modulus? Remains same. Two. Okay. Modulus remains same. Argument, now argument changes. This lies in the second quadrant. Okay. This lies in the second quadrant. So because X is, real part is negative, imaginary part is positive. So this is a number that lies in the second quadrant. Argument has to be between pi by 2 and pi. Correct. Argument has to be between, see, it's a second quadrant angle. One So it will be greater than 90, less than 180. Okay, this is your argument of Z. This is that point Z. Okay, so but when you do tan inverse of B by A, tan inverse of B by A is root 3 by -1, so minus root 3. Okay, but this will give you a negative value. This is minus pi by 3 you will get, but this is, so you will get minus pi by 3 because tan inverse will give you this value. Tan inverse will give values only between minus pi by 2 to pi by 2. So now this is minus pi by 3. Minus pi by 3 plus pi. Okay, so this is 2 pi by 3 or 120 degrees. So this is the modulus. Modulus is 2. Argument is 2 pi by 3. Understood? Many times some teachers, they wrongly teach that argument in all cases is minus b by a. That's a mistake. Tan inverse tan inverse b by a. That's a mistake because all that you will get values only between minus pi by 2 and pi by 2 if you do that. Next, third question. Did you understand this part? Third question. Z is -1 minus root 3i. So which quadrant does it lie?
Third, sir.
Third quadrant. Very good.
-5.
Modulus is under root of -1 the whole square plus minus root 3 the whole square. You again get 1 plus 3, which is 2. So modulus remains the same. Now argument, now you tell me. You get tan inverse of minus root 3 by -1. So you get tan inverse of root 3. That is wrong because here we'll plot 1 second. This is that point -1 minus root 3i. Okay, now the principal values of the argument is minus pi to pi. So this will be the angle. This will be the argument. However, you get here tan inverse of root 3. Tan inverse of root 3 gives you the angle in the first quadrant because it's a positive. So tan pi by 3 will give you root 3. So tan inverse of root 3 is pi by 3. However, the angle you need is in the third quadrant. So it has to be less than minus pi by 2 and greater than minus pi. So it has to lie between minus pi by 2 and pi. So what do? You have got this angle. You want this. So you subtract. Whenever you go clockwise, the angle will have a positive sign. Whenever you go anti-clockwise, angle will have positive sign. Whenever you go clockwise, angle will have negative sign. So minus pi minus pi. So you get minus 2 pi by 3 is the argument. Okay. The same thing is the formula, but I am explaining with logic so that you may remember formula or may not remember. Sometimes in confusion we remember wrong, then it will go. So, but logically, if you think, you will get the right answer. Okay. So minus 120. It has to lie between minus 90 and minus 180. So minus 120. It's correct. Last part, z is equal to 1 minus root 3i. Okay. 1 minus root 3i. So this is the argument. Argument is always taken with respect to the positive real axis. Always measure. So now because we are measuring clockwise, your argument has to be negative. So let
Minus
us,
pi by 3.
yes, minus pi by 3. Very good. Modulus remains same. Argument is tan inverse b by a. Now tan inverse b by a. Now this is tan inverse minus root 3, which is minus pi by 3 minus 6. So this is how we find argument. Now you don't have to add plus pi or minus pi because it is correct. It is fourth quadrant angle. It is minus pi by 3. Okay. So we took one problem and did in different way. Now a general one. One more we'll do. Let us see. Z is minus 1 minus I. Now tell me, what is the modulus? What is the modulus? Mod Z is equal to under root of a square plus b square. B is also minus 1 here. So under root of 1 plus 1 equal to root 2. Then argument tan inverse b by a tan inverse 1. However, this gives you pi by 4, but you cannot get pi by 4. Which quadrant this lies in?
The third quadrant, you should subtract pi.
Yes, very good. Got it. Very good. So that's the argument. You subtract pi, so you get minus 3 pi by 4. All right. So this is about modulus and argument. So you can now do any of the problems based on this from your textbooks. So I covered all the possibilities. So next is representation of a complex number. Okay, representation of a complex number. So yeah, there are different representations. See earlier, see there are 5 forms of representation of a complex number. I'll copy this. Hmm. Okay. So a complex number can be represented in the following forms. Algebraic form, graphical form in the Argand's plane, polar form, Eyeless form, and vector representation. Vector representation we'll not discuss now. After vectors are over, that is one. But I will just give an idea. Algebraic form is what we have already discussed. So the algebraic form of complex number is this: a plus ib or z is equal to x plus iy. This is the algebraic form which we have already discussed, which has a real part plus I times imaginary part. Basically, real part plus I times imaginary part. This is a complex number. So this is the first representation. Okay. Now the second representation is graphical form. So as a point in an Argand's plane. So this is the graphical form. So this is the real part of Z. This is the imaginary part of Z. This is the origin 0 plus I times 0. Now any point P or complex P represents the complex number Z. All right. It's like this. And Z is x plus iy. This is the algebraic form. In the Um, okay. In the graphical form, it is represented as a point. Now this distance is x and this distance is y. So this is p z. It is x plus iy. You can also represent it as x comma y. Or you can simply say complex number z. So it is representing a point. So this is a graphical representation of a complex number. This is the algebraic form. This is graphical form. Next is polar form. This is a very important form. Okay, polar form of a complex number. This is a very important result. It comes from this. We will take the same figure. Polar form of a complex number. So in this, now you just see this, how I write this. Observe very carefully. Now I join these 2 points. I'll delete this, I'll draw a straight line. Okay, this is a straight line. Now, what will be this distance OP? OP distance, let OP be equal to R. R is under root of x square plus y square, correct? Because this forms a right angle triangle. Okay, if you mark this point as A, this forms a right angle. OAP is a right angle triangle at A. So this will be hypotenuse. Now, what does this give? This is modulus. So this is nothing but modulus of z. All right. This is modulus of z. Modulus of z is distance of the point from the origin. That is modulus. I will not draw such a thick line. It will be. Okay. This is modulus of z. The distance from the point P to the origin. This is modulus of z. And what is this argument? Argument theta. Okay. Now, cos theta is x upon r. Sin theta is y upon r. Oh, sorry. Cos theta is x upon r, correct. Sin theta is y upon r. All right. adjacent by hypotenuse is cos, opposite by hypotenuse is sine. So now let us see how I write. Z is x plus I y. Now I multiply and divide by under root of x square plus y square. Okay, I will write one more step. That is, in effect, I am dividing by r. X plus iy upon r, the modulus. So I get r times x upon r plus I times y upon r. Now, no matter where x is both positive, x, y both are positive, it will be in first quadrant. If x is negative, y is positive, it will be in second quadrant. If x is negative, y is negative, it will be in third quadrant. When x is positive, y is negative, it will be in fourth quadrant. But in all cases, whatever the argument theta is, okay, whatever the argument theta is, this argument, um, sine of this argument, cos of this argument will automatically give you this result. Okay, so now z, I will write this as r into cos theta. X by r is cos theta plus I sine theta. This is the polar form. This is the polar form of the complex number. Okay. This is also called as modulus argument form or modulus amplitude form. Mod amp form or mod arg form. So this form, it's a very important and useful form. Sometimes they write r cos theta plus I times sine theta as r cis theta. There is nothing called as cis in the trigonometry. But when we write cis, it means cos theta plus I sine theta.
So if we substitute theta, will we get the original complex number?
Yes, yes, we get that. From there only we are deriving. No? So now this is the polar form, very important and useful form. So now we will do. So let us take the previous problems only. Numerical problems. Convert the following numbers into their polar forms. So the first one, z is equal to 1 plus root 3i. What did we get? modulus of z, which is r, was 2, and argument we found was tan inverse root 3, which is pi by 3, okay, or 60 degrees. So therefore, polar form is z is equal to 2 times cos 60 plus I sine 60. All right. Now you substitute and see, you will get this. Cos 60 is half plus sine 60 is root 3 by 2 multiplied by 2. What do you get? 1 plus I times root 3. That's what you get here. Okay.
Yes,
So
sir.
this is the modulus amplitude form or polar form or modulus argument form. The same examples we'll take one by one. Minus 1 plus root 3i. We found mod z equal to r, which is 2, and we got argument. What did we get? This is second quadrant angle. We
2 pi
got
by 3.
2 pi by 3. Very good. Therefore, polar form of z is z equal to r times cos 2 pi by 3 plus I times sine 2 pi by 3. When you substitute, cos in the second quadrant is negative. You will get minus half. Sine in the second quadrant is positive. You will get root 3 by 2. When you and r is 2, you substitute and multiply, you get back this. Okay, you get back the original. So this is the polar form. They are same numbers, but we are writing in different forms. This number and this number are same, but we are writing this in modulus amplitude form, and this one is in the algebraic or arithmetic form. Third case, mod z equal to minus 1 minus root 3i. Please tell me. The modulus we had found out was
2, sir.
2. Argument we found out was,
Minus 2 by 3.
yes, is theta. Minus 2 pi by 3. Therefore, polar form of z is z equal to 2 times cos minus 2 pi 3 plus I times sine minus 2 pi by 3. Okay. All right. Then fourth.
Sir, over here, but cos of minus theta is equal to cos theta and sine of minus theta is equal to sine theta. So,
Right.
wouldn't it be similar to the second?
Sine of minus theta is minus sine theta.
Okay, yes, sir, yes, sir.
Okay. All right. Next. Now z is 1 minus root 3i. Mod z is 2. Argument of z, what was it? Minus pi by 3. So polar form or modulus amplitude form cos minus pi by 3 plus I sine minus pi by 3. Okay, the last one that we did, z is equal to minus 1 minus I. Mod z we had found to be under root 2. Argument of z we found to be uh, minus 3 pi by 4. Therefore, polar form root 2 times cos minus 3 pi by 4 plus I times sine minus 3 pi by 4. Okay, got it? Polar form of the complex number. Clear? Next, which is the next type? Eyeless form. Very useful form, huh? Extremely useful form. Then after I do this, I will talk about the algebraic operations in different forms. Uh, Eyeless form. There is a very interesting result for Eyeless form. Euler showed that this Euler's form of a complex number, and there is an Euler's formula e power I theta. E is exponential function. E power I theta is cos theta plus I sine theta. How do you prove this? There is a proof of this requires some knowledge of calculus, but I'll just show it graphically for you. Maybe GeoGebra. Or, okay, I have already done it in.
So what is E, sir?
Acha. Uh, E is an irrational number. I'll just explain that to you. You have not attended functions, na? So, but I'll explain that. Just a second. Uh, So E is a number. This existence of this number E is a very special. Just like pi is a number, irrational number. E is an irrational number, 2.71828, so on. We just take 2.718 as E. We truncated there, but actually it is this number. It does not have a an end, meaning it is a non-recurring decimal, non-terminating decimal. Just like pi we understand, right? Pi is defined as, the ratio of the circumference of a circle to the diameter. That is defined as pi. So 2 pi r, we get that concept of 2 pi r because of pi. For any circle you take, the ratio of the circumference to diameter is a constant. So based on that, they found this value pi. Similarly, E has to do with an exponential, a series, power series. We'll do that. This you have to know some little bit about calculus, but E is an irrational number. Okay. Now, once you know that, now I'll just try to show. Okay, I'll have to explain to you some things first. Yeah. How do you get this Euler's formula? The scope of it is little beyond what we have learned now. You have to have a little idea of calculus, not much, little differentiation. But right now, you just have an idea of this. Later, we will, when you come back to this after learning calculus, it will make so much sense. However, I'll give you a graphical representation for this. There's a proof. What I'm showing you right now is a proof of how e power I theta is equal to cos theta plus I sine theta. Okay. Now this is a very, very useful form, extremely useful form. You can solve problems so quickly because of this, if you learn this. Now let us see. See, there are Maclaurin series of functions. Maclaurin series is derived from a Taylor series. Now, you see the sin x. Sin x can be approximated to a series expansion. This series, x minus x cube by 3 factorial plus x power 5 by 5 factorial minus x power 7 by 7 factorial plus x power 9 by 9 factorial minus x power 11 by 11 factorial, so on. Now, how is that true? Let us see this. I'll just show you by a grapher. So now you are able to see the full graph. We know that this is the graph of sine function. Okay, I'll put it in a projector mode. How do I close this? So this is the graph of a sine function. Now you see, I'm just showing how that series, Maclaurin series, is a equivalent to sine. You just see. Now sine x, if I just take the first term of that series, this is the first term, sine x is x. Okay, so when I take the first term, I get a straight line. So these two are not equal. Sine x is equal to x only in a very close vicinity of 0, otherwise not. Next, I go to the next function. You see, x minus x cube by 3 factorial. You see this? So this graph, this is a cubic graph, a polynomial graph. Now it is equal to sin x in this range, in close to 0, uh, and between minus pi by 2 to pi by 2, for most part it is coinciding. Next, I have increased the number of terms to 1, 2, 3, 4, 5, 6 terms. Okay. Now you see this graph, this polynomial is now so much overlapping with sine graph. I go to the next. Okay, keeping this, I go to the next. Now another 3 terms I added. So now I see this is completely coinciding with sine graph up to here. So now as you increase the number of terms to infinity in the series, the graph of that series will completely coincide with sine. So this is an amazing revelation in mathematics and graphs, this Maclaurin series expansion, Taylor series, and from there Maclaurin series, an application of derivatives you will learn. Similarly, now this was sine series. Now look at cosine series. Okay, cosine series. It is 1 minus x square by 2 factorial plus x power 4 by 4 factorial minus x power 6 by 6 factorial, so on, right? So this is cosine. Y equal to 1. It doesn't have any match. Okay, it doesn't have any match. It is just like a line. It is just equating. So first term, if you do only at x equal to 0 or very close to 0, there is some match. Otherwise, there is no match. But when you take the second term, 1 minus x square by 2 factorial. So maybe between pi by 4 and minus pi by 4 to pi by 4, around that, you see there is a close match, of course. Now let us go to more terms. So next term, now you see the overlap has increased, and you go further, again overlap is increased. Go further, again overlap is increased. So like that, if you go for infinite terms, again this series will be equal to cosine series. This is to give you a visual expression. This is not a mathematical proof, but to explain to you how this series represents the sin x can be approximated by this series. Similarly, exponential. All right. See, 1 term, 2 terms, 3 terms, 10 terms, up to 10 terms. So exponential curve. This is the exponential graph of an exponential function. You take y equal to 1, it doesn't meet only at x equal to 0. It is improper approximation. Y equal to 1 plus x, it's a tangent to the curve at 0. Yeah. No, y equal to 1 plus x square by 2 factorial. At some small portion, there is an overlap, otherwise, no. Then go to more terms, you get an overlap. More terms, you get an overlap. And finally, you see, so much overlap. So much overlap. Practically, the overlap is, let us see where it is. Practically on the right side, you just can't make a difference. Yeah, slight difference when you zoom in. Okay, but it's an overlap. Okay, got an idea? So these are series expansions which are very, very useful. I'll just conclude with this proof now. Now, instead of this, I take this e power x, all right, and I substitute, instead of x, I substitute I times x, where I is the unit complex number, unit, imaginary unit. When I substitute that uh, in in this series, I get this is I square, I cube, I power 4, I power 5, I power 6, I power 7, which I explained to you previously. I square will be minus 1, so you got minus 1. And then I cube will be minus I, so you get that minus I power 4 is 1, I power 5 is I power 6 is minus 1, I power 7 is minus I, so on. Now these terms go on like this. Now I separate it out. Terms containing I and terms that do not contain I. When I separate out the terms that do not contain I get 1 minus x square by 2 factorial plus x power 4 by 4 factorial minus x power 6 by 6 factorial. And if I pull out this I get this x by 1 factorial minus x cube by 3 factorial and so on. Okay. This is nothing but your cos series. This is nothing but your sine series. That is how you get this e power x is cos x plus I sine x. Okay. So this is the basis of the Euler formula. So now, very simple, this Euler formula we'll conclude here. Now Z uh, is, you can write x plus Iy, which you can write as r times cos theta plus I sine theta, that is polar form. Now the same thing, because cos theta plus I sine theta is e power I theta, you can write the complex number as r e power I theta. This is the Euler form. Euler's form of a complex number. All right. In CBSE, Euler's form is not introduced. However, for all JEE questions and any entrance exam questions, Euler's form will be so useful. I will explain in the next class. Algebraic operations. Next class will be this. Algebraic operations using various forms of complex numbers. Okay, you will see that the first form and the graphical form are useful for addition, and you know algebraic and graphical, very useful for addition and subtraction. Now polar form and Euler form, very useful for multiplication and division. So this is what I'll start with and complete the remaining exercise on CBSE in the next 3 classes. Any questions?
So you said you'll give homework for the 3 days.
Okay, I'll upload. Right now, I think trigonometry you just cover. In the meanwhile, I'll try to upload because you have just done various forms. So right now you complete the trigonometry if you have not completed. Because if I give you homework on complex numbers with the basics, I'll try to give. I'll try to upload an assignment. Okay, and I'll extend that trigonometry uh, assignment timing. All right. Any other question?